Hello, today we're going to be discussing electrical circuits, part 1, basic electrical circuits. There will be a series of tutorials in here, and they'll lead one after the other. In this particular one, we'll discuss the two types of current flow theories. We'll discuss what it takes to be a circuit, a little bit of the terminology that we'll be using in later tutorials. So to get started, we're going to talk about the electron flow theory. It is actually the most widely recognized as being correct. It has actually been proven in physics that that it is the correct one. Electrons are negatively charged particles, and since they're negatively charged, that is our current flow, the free electrons. So current flows from the most negative part of the circuit to the most positive point in the circuit. And the following tutorials that we'll be doing in this series, we will be using the electron flow theory. Now, the other theory that we have is the conventional current flow theory. It's much older than electron flow theory. It was the first of them, and it simply states that the current flows from the most positive point in the circuit to the most negative point in the circuit. And so most electronic circuits that are DC use the negative terminal as the ground, and so the positive is considered to be above ground or hot. And so it was easier for most people to think of something as flowing down rather than up. And an automotive electrical system is a very good example of that type of circuit. Now, a lot of our symbols that we use in our schematics, especially for our semiconductors, they use arrows on them, on the symbols, and whenever they were made, we were going by the conventional current flow theory, so the arrows were pointing in the direction that they thought that the current flowed in. And so if you're using electron flow theory, using it, the current would flow against the arrow, or the arrow would be pointed towards the more negative side of the circuit. Now, for a basic electrical circuit, first off, we have to have a complete path. Has to exist before current can flow. So it has to exit some type of a power source, and it has to return full circle to that power source. Otherwise, the current cannot flow. So some of the things that we have to make an actual circuit that we say that we have to have would, of course, to start off with, we'd have to have a source of power, an energy source. And then we would have to have a path for the current to flow. That would be our conductors, our wires. The conductors inside the wire, the insulators on the outside. It is designed to hold the current inside the conductor. And then we need the load. We have to have some type of load, or we have an extremely high amount of current flow, a lot of heat, and this would be very bad. And then, of course, we need a controlling device. A controlling device can be something like a switch, a relay, a solenoid, even a PLC. But we have something to control the circuit, to turn it off and turn it on. Now, when we have that complete path and current can flow, we call that a closed circuit. And if we have an open or a break in that circuit where the current can't flow, say like a light bulb is burned out or something to that nature, we refer to that as an open circuit. A good way to look at it is a simple light switch. A light switch is a controlling device, and whenever you turn it on and energize the lights and they come on, we have a closed circuit and the current can flow. That's why the lights come on. When we turn that switch off, then we create an open or a break in that circuit, and it becomes an open circuit. Current cannot flow. The open is at that switch, and that would be considered an open circuit. Now, we have another condition that we need to talk about, and that's when we have a circuit with little to no resistance, no load in there. It could be that we have a pathway for a conductive pathway for the current to flow. Conductors become connected leading to and from the power source. It can be maybe an unwanted path to a chassis ground or the ground. We can even have an unwanted path to another circuit occur, and we'd refer to that as a short circuit. Now, a short circuit is the least common issue you're going to have working with electricity. However, it is also the most destructive, because when we have a short circuit and very little resistance, we have an extremely high amount of current flowing. We have maximum current flow. So getting into some of the quantities, we'll talk about the Coulomb first, and it is the quantity of measurement for the electrons. 1 Coulomb is going to contain 6.25 times 10 to the 18th electrons. We use the SI unit of the uppercase C to designate the symbol for a Coulomb, and the charge transferred by a current of 1 amp in 1 second is equal to 1 Coulomb. The next term that we're going to talk about is the ampere. Now the ampere is the part that moves. That is our current flow. That's our free electrons moving. And the ampere is equal to 1 Coulomb per second, and it is the measurement of the amount of electricity or the current flowing through a circuit. We use the symbol for the ampere for I in our algebraic formulas, the I for the intensity of the flow of current, and A for ampere. The uppercase A is the symbol we use when we're given the amount of amperes in a circuit. Say if we had 3 amps in a circuit, we would designate that by putting the number 3 with the uppercase letter A right after it. And as you noticed, I called it an amp or amps. More times than not, we're going to shorten or abbreviate ampere into amp or amps. The volt. The volt is our potential energy difference between 2 points. It's a pressure difference. If we have a piece of wire, we can't measure volts on there because there's no pressure difference. The same amounts flowing through that entire length of wire. We can measure a potential difference across the post on a battery. Even in a wall socket in an AC circuit, we can measure the potential difference there. We can measure the potential energy difference between across any load that we have in the circuit. And so the volt is a potential difference between 2 points of a conductor carrying a current of 1 amp when power dissipated is 1 watt would equal 1 volt. Voltage, again, is the force or the pressure that pushes or causes the current to flow through a wire or a circuit, and we often refer to it as electrical pressure. We also refer to it as electromotive force. We usually shorten that down using the uppercase EMF for that. Symbol for voltage is we use the V for volt. So if we had 12 volts in a system, like on an automotive car, we would designate that with the number 12 followed by the uppercase letter V. And then sometimes in our algebraic formulas, especially, we'll use the letter E for our electromotive force. The ohm. The ohm is the opposition to resistance. It's the unit of resistance or opposition to the flow of current. The symbol that we use for the ohm is the Greek letter omega, and the letter that we use in our algebraic formulas is the uppercase R for resistance, and 1 ohm is the amount of resistance that will allow 1 amp of current to flow when we have 1 volt of pressure applied. And the watt. The watt is our biggest concern because that's the amount of work that we can do. That's the amount of work we're doing. It's the measure of the amount of power that will be used in the circuit. The symbol that we use for watt is the uppercase W for a watt, and we use the uppercase P for power in our algebraic formulas. We'll get to some of these algebraic formulas in a later tutorial. Now the watt, again, is the amount of work that can be done. Not necessarily the amount of work we are doing, but it's the amount of work that we can do. That concludes this tutorial. I hope you'll enjoy me. Will join me for some of the later tutorials. Thank you.